Well, hello and welcome back to another exciting round of geometry. We are in lesson 11-3, proving and applying the congruence criteria. So let's take a quick look at our learning targets, and then we'll hopefully piece together what we looked at in 11.1 and 11.2, and then even go back a little bit further into 9.1 and 10.1. So our learning target says prove that congruence criteria follow from the definition of congruence, and then we will use the congruence criteria in simple proofs. So again, rate these from 1 to 5, 1 being very little understanding of what it's asking us to do, 5 feeling very comfortable of what these learning targets are asking us to do. But before we dive into this any further, learning target 1 says prove that congruence criteria follow from the definition of congruence. So I wanted to remind us there are actually 2 definitions of congruence. So I put them down here. Congruent definition 1, the first definition we learn is that figures that have the same measure. Pretty basic. For 2 segments to be congruent, they have the same length. For 2 angles to be congruent, they have the same degree measure. And that makes pretty well good sense for us. And then when we started studying in activity 9 and 10 with our transformations, we uncovered another definition. So the second definition of congruency is figures in which one maps onto the other by composition of rigid motions. And so go back to the learning target. We're going to prove that the congruence criteria that we learned in lesson 11.2 and found over here, we're going to prove that that criteria follows the definition, the second definition of congruence, that a series of rigid motion maps one onto the other. So these are the shortcuts that we learned in 11-2. There's a couple other. We're going to see those in 11-4. So side, 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 that's what the 3 S's stand for, states that triangles are congruent if all 3 sides in one triangle are congruent to the corresponding sides in the other. You can actually see that on item 1 here. But the way it would look is we would say that these 2 triangles are congruent if 1 pair, 2 pairs, and 3 pairs of corresponding sides in one triangle are congruent to their corresponding sides in the other. And remember, we use these marks to denote which sides in each triangle are actually congruent in the other. The other shortcut is side angle side. Notice I'm using the term shortcut or criterion. That's a fancy word for it. Criterion just really means requirements. And we learned in lesson 11.1 and 11.2 that there are shortcuts to proving 2 triangles congruent. We don't actually have to find out if all 6 pairs of corresponding parts for one triangle are congruent to the corresponding parts in the other. So we figured out that there are shortcuts or criterion. The next criterion, triangles are congruent if 2 sides and the included angle, and that's very important here, included angle of one triangle are congruent to 2 sides and the included angle of another. So the way that would look is, again, 1 side, 1 pair of corresponding sides, 2 pairs of corresponding sides, and then the question is, which angle is considered included? Well, it's really the angle that is a part of the 2 sides that are marked. So this angle in the top, I guess if you would say, of the triangle would be considered the included angle because it's a part of both sides here that are congruent to corresponding sides in the other triangle. So this is one representation of side angle side. And then the last shortcut we're going to look at least for this lesson, is angle side angle. Kind of the opposite of the one we just saw. Instead of 2 sides in one angle, we're going to look at triangles are congruent if 2 angles in the included side of one triangle are congruent to 2 angles in the included side of another. So now we're saying if, for instance, this angle was congruent to this one, there's 1 pair, and this angle is congruent to this one, there's 2 pairs of angles congruent in both triangles. And the included side would be the side that is a part of both of the angles that are marked. So this would actually be considered the included side. So for these 2 triangles, or suggesting that these 2 triangles are congruent, if two angles in their included side is congruent to these two angles in their included side. That's what we're suggesting here. So without further ado, let's take a look at our actual lesson. You can use the side, angle, side, or angle, side, angle congruence criteria as shortcuts. That's why I was using that word, to show that two triangles are congruent. In other words, we don't have to use all 6 pairs of parts. We can just use 3. In this case, 3 sides. In this case, 2 sides and an angle. In this case, 2 angles and a side. In order to prove why these criteria work, you must show that they follow from the definition of congruence in terms of rigid motions. That's what we were talking about, the second definition there. So at this time, if you would roll over to page 155 and draw a line right below H. And again, what the line tells us is to pause the video, try to work 1 through H before playing through and seeing my answers and the explanation of it. So hopefully you took a second and try this one on your own. Maybe the wording confused you a little bit. To justify the side congruence criteria, consider the 2 triangles below. Notice these 2 triangles are marked very similar to the sample one I gave you over here. A said, what given information is marked in the figure? Line segment AB is congruent to DE. Line segment AC is congruent to DF. Line segment CB is congruent to FE. So hopefully you can see, again, depending on how many marks, that's what we're suggesting, what parts we're actually suggesting congruent. So segment AB had 1 mark on it. Segment DE had 1 mark, so we're saying that those 2 segments specifically are congruent. B, based on the definition of congruence, we're talking about the second definition. What do you need in order to show that triangle ABC is congruent to triangle DEF? To really verify not just the side congruence criteria, but just the fact that these 2 triangles are congruent, there should be a series of rigid motions that maps triangle ABC onto DEF. And notice I said rigid motion, because we know rigid motions preserve size and shape. So if I take triangle ABC and I perform a series of rigid motions, somehow moving in and placing on top of DEF, if it maps onto triangle DEF, I know that the 2 triangles are congruent. Item C says it is given that side AB or segment AB is congruent to segment DE. What does this tell you? I said, again, we're really trying, I know some of you probably said they have the same measure. We're really trying to get into this second definition of congruency here. So I said that line segment AB can map onto DE, and that's what they want us to do on part D. Show that, and this is my drawing, and it actually looks very similar to one you'll see on F. Think about it. Hopefully we're imagining this triangle here rotating, and A is swinging out all the way to get to D, and B is swinging all the way to get to E, such that line segment AB maps onto line segment DE. And notice it says, assume that the sequence of rigid motions does not map point C to F. They don't want you to go ahead and put triangle ABC on top of triangle DEF. Really just trying to extend our understanding of rigid motions here. So E then says which points coincide, and those are the points that match up, if you will, or map onto the other. And then it says which segments coincide. So what we're suggesting here is not only the points, but the segments that are between the 2 points that coincide. So A mapped to point D and B mapped to point E, so they are essentially mapped onto each other. Therefore, line segment AB coincides or is on top of line segment DE. And then F asks us to mark the line segments that you know are congruent in the figure. So let's think about this. We're suggesting that maybe a rotation, that's probably what I would safely assume, a rotation took this triangle such that line segment AB mapped onto line segment DE. And now when we see in the picture, the fact that AB and ED were the same length, it makes sense. They can map on top of each other because this one little mark here suggests that they are congruent. So as we press forward, G then asks, based on the figure, how is line segment ED related to line segment FC, and why? So I said that line segment ED is the perpendicular bisector of FC, and it's all hinging on this new theorem over here. The perpendicular bisector theorem states that if a point lies on the perpendicular bisector of a line, if and only if it is equidistant from the endpoints of the segment. So how do I know ED is the perpendicular bisector of FC? So let's look at it. Now we could obviously safely assume that that's a right angle, but again, assumptions are a little dangerous in geometry. Well, how do I know E is the same distance from F and C? Well, look at the markings between E and F. There's 3 marks here that tells me that this side is actually congruent to line segment BC. In other words, the distance from E to F is the same as from B to C, or the distance from E to F is the same as from E to C. So if a point is equidistant from the 2 endpoints, then that point, in this case E, is on the perpendicular bisector, which also means that point B is on the perpendicular bisector, and point D is on the perpendicular bisector, and A is on the perpendicular bisector. So the reason I know that is that, again, that distance from E to C is the same or equidistant from E to F. Well, if ED is really the perpendicular bisector, we know that reflections hinge on this idea of a perpendicular bisector. So H says, consider the reflection, there it is, of triangle ABC across ED. So now we know that if ED is the perpendicular bisector, C can actually map onto F. We already know B mapped onto E and A mapped onto D, but C can map onto F. So it says, what is the image? Image is the result of that reflection of triangle ABC. So where did A map to? Well, A mapped to D. Where did B map to? E. And then the last point after the reflection, C mapped to F. So that's why I said triangle DEF in that order. And I'm going to write this note. Order matters. Right? That's what lesson 11.1 was all about, how the order matters. So we have to be very specific in where each point maps to in these triangles. Now, as we press on, the text kind of demonstrates or shows us a little bit these rigid motions that we've been suggesting the whole time. So if you would go to the bottom of the page and draw a line, and then try to complete 2 and 3 on your own before playing forward. So the argument we saw in item 1 does suggest that there is a series of rigid motions that map triangle ABC onto triangle DEF, and we see that here. Step 1 would be a rotation such that C ends up here. We know point B will map here, and point A will swing all the way over here. It says specifically the sequence is a rotation followed by reflection. And number 2 in the proof, is it important to know exactly, and I underline that word exactly because I think that's important, which rigid motions map line segment AD to line, or AB to line segment DE? And I said not necessarily. Not to say that it's not important. It's helpful to know how a rigid motion proves congruency, but the exact order is not necessarily required. Or for that matter, you might be suggesting that there is a translation involved here. So maybe the exact sequence of rigid motions is not as important as long as we know that there are rigid motions that can prove that this triangle ABC maps onto triangle DEF. And then 3 really just emphasizes, this question really emphasizes how a perpendicular bisector coincides with this idea of reflection. And we study this a little bit more using GeoGebra and how it really is a perpendicular bisector. So if line segment ED is a perpendicular bisector of FC, then the distance from F to ED, so the distance from F to ED is equal to the distance from C to ED. Therefore, ED is the line of reflection. So knowing that ED was a perpendicular bisector of FC, and the distance from F to that line is equal from C to that line, therefore ED is acting as a line of reflection. So just really, again, emphasizing how perpendicular bisector, that idea and the theorem involved with it really coincide with reflections. So that's proving side, side, side. So we know the 2 triangles are congruent. And initially, we only knew that 3 pairs of corresponding sides were congruent. But now taking the definition of congruency using a series of rigid motions, we know that side, side, side is enough information, enough criteria to prove two triangles congruent. Now let's press on to our next criterion. Number 4 says to justify the side angle side congruence criteria, consider the two triangles below. Notice we have the same triangles as on the previous page, but now the markings are a little bit different, suggesting that we don't know all three sides are congruent, but we know that two sides or two pairs of sides of corresponding parts and one pair of angles, again, corresponding parts, are congruent. So if you would, scroll down and draw or not scroll down probably, below E, draw a line, pause the video, try to complete this. Hopefully your understanding of what this lesson is looking for is increasing before playing through. So now we're proving the side angle side. Remember, it's two pairs of corresponding sides and the included angle. We're suggesting that that is enough to prove that triangle ABC is congruent to triangle DEF. So A, what given information is marked in the figure? Angle A is congruent to angle D, as well as line segment AC is congruent to DF, and line segment AB is congruent to line segment DE. So again, two pairs of sides, corresponding sides, and a pair of congruent corresponding angles. B says the proof begins in the same way as in item 1, and not to confuse you here, but we're using the same idea of rigid motions to map one triangle onto the other to show that these shortcuts really do work. And again, it all hinges on the definition, the second definition of congruent. And they're really highlighting the fact that line segment AB is congruent to DE. So if line segment AB is congruent to line segment DE, we know that line segment AB can map on top of line segment DE. So that's why this drawing continues to show back up, is because line segment AB is the same length as DE. So we can map those or kind of push those up side by side. So C said mark the line segments and angles that you know are congruent. And so now we have a pair of angles that are congruent. And this is what D really suggests, really focusing on these pairs of angles. D says suppose you reflect triangle ABC across ED. So we're going to take triangle ABC, use line ED as a reflection or line of reflection, and map onto triangle DEF. What is the image of AC? We want to know, where does AC map to in the reflection? Well, you probably already know that it's going to map to DEF because we're using the same pair of triangles, but we want to just take this idea of why these two angles really change the idea here. So what is the image of line segment AC? Why? Well, we know it's line segment DF, but now instead of viewing ED, line segment ED, as a perpendicular bisector, think about what it's doing to these two congruent angles. This is actually the converse of the definition of angle bisector. So what ED is doing, this segment, it's cutting this angle CDF into two congruent angles. That's another way of looking at it. You can kind of zoom out a little bit, and maybe you can think that if these two angles really are congruent, and now we're viewing this as one larger angle, then ED, this line segment, or BA, another way to look at it, is bisecting angle FDC. So if these two angles are congruent, then this angle that we called angle A can map onto this angle because they're the same measure. And again, it all hinges on our second definition of congruence. So E then says, when you reflect triangle ABC across ED, can you conclude that the image of point C is point F? Well, since line segment AC maps to DF and AC is congruent to DF, point C has to map to point F. We know that the distance from C to A is the same distance as F to D. That's what these marks mean. And because these two angles that are on these two line segments are congruent, then we can't adjust the angle at all. We know that point C, being locked in kind of by this angle and this distance, point C has to map to point F. Again, same diagram, same rigid motions. We're just now viewing it with two sides and an included angle and how that affects our understanding of triangle congruence. Now let's finish it up looking at the angle side angle congruence criterion. Notice now instead of 3 sides or 2 sides in one angle, now we have 2 pairs of angles shown to be congruent and 1 pair of sides congruent. So if you would, go and draw a line at the bottom of the page. Again, try this on your own, and hopefully this last one is really making more sense. But again, think about how the information can differ a little bit now that we have 2 pairs of congruent angles. So even in completing this one, and I've done this before, I'm realizing something new here. So let's go back to 5A. What given information is marked? Think about what's marked now. We don't exactly know that the distance from C to A is the same distance as F to D. Again, it's not marked in the diagram. They definitely look like the same distance. And likewise, the distance from C to B is, we don't know if it's necessarily the same distance as E to F. Now, again, it looks like it, but what we do know is that angle A is congruent to angle D. Line segment AB is congruent to line segment DE, and angle E is congruent to angle B. So remember, for 2 angles to be congruent, it has nothing to do with the length of the rays. So these 2 angles could actually be congruent even though the length of this ray is not the same length as that ray. Or the length of this ray is not the same length, but the 2 angles can still be congruent. So think about it. And I'm just like, it's making so much more sense to me as I'm doing it even in this video. If we know that angle D is congruent to angle A, this ray could really just keep extending forever and ever and ever. Same thing here. This ray could really keep extending forever and ever and ever. But if angle B is the same measure as angle E, when angle B, we extend this ray, at some point it's got to intersect with this other angle. And that's what we call point C here. Likewise, on this other triangle, when ray EF keeps extending, and when we find that intersection point, we label that F. So it's really, these rays could keep going on forever and ever, but when they intersect at a very similar location on both triangles. So even if we don't know the length of AC compared to the length of DF, the fact that these 2 angles and what they're doing when they intersect, creating these third vertices of the triangle, is what's helping us prove these 2 triangles congruent. I thought that was very interesting to point out. Probably just got a little ahead of myself on this one, but very similar on this one. We don't know that the distance from F to E or F to D is congruent to C to B or A to C. So that's what we're trying to figure out. So mark the line segments and angles that you know are congruent. Here we go. And then D says, suppose you reflect triangle ABC across ED. What is the image of AC? Let's start there. Well, the image of AC maps to, again, DF. And it's not because we know that the distance from A to C is the same as D to F. It's because the angle of A is congruent to the angle of D. So then I should be able to map angle A on top of D. So where will AC end up? Well, on top of DF. And likewise for BC. Again, we don't know that the length of BC is the same as EF. But angle B is congruent to angle E, so angle B can reflect and land on top of angle E. And it's all dependent on the fact that ED or BA, this line segment here, is the angle bisector to this angle and also this angle. E says, when you reflect triangle ABC across the line segment ED, can you conclude the image of point C is point F? Yes, because of what we said in D. AC maps to DF and BC maps to EF. Well, look, C mapped to F here and C mapped to F here. Therefore, C has to map to point F, suggesting that the 2 triangles really are congruent. That triangle ABC, with what we know, does map on top of triangle DEF. Mind-blowing here, so keep that in consideration. Now let's move on to our last page here. Example A, we actually start seeing, don't forget that these triangles are from trusses from, I believe, a recreational hall, Greg Carpenter, in fact. So Greg knows that point X is the midpoint of JK in the truss shown below. He also makes measurements and finds that the length of JL is congruent to KL. He must prove to his boss that triangle JXL is congruent to KXL. And so now what we're doing is we're seeing how we could not just prove it by a series of rigid motions, which could sometimes be debated. We're actually going to write a 2-column proof to show that the two triangles are congruent based on this information. Now, the proof is already done for us, but I kind of want to explain it a little bit. So if we know X is the midpoint of JK, which is statement 1, look at statement 2. How do we know that the length of JX is congruent to KX? Well, if X is the midpoint, we know that a midpoint, by its definition, divides a segment into 2 congruent segments. Therefore, JX is congruent to KX by the definition of midpoint. And then in item 3, we know that JL is congruent to KL because Greg, actually found that information out. So look here, we have 2 pairs of corresponding parts congruent. Well, we need a third pair of sides, or we need a pair of angles. And so look what they figure out in statement 4. This is rather interesting. Line segment LX is congruent to line segment LX. Now imagine these 2 triangles, JLX and KLX, butted up against each other. One of the easiest ways to find if 2 things are the same length is to put them back to back. Well, LX is in fact congruent to itself, and it seems silly that we have to say it, but really, congruence is reflexive, or this is known as the reflexive property, which is found on page 26. So for something to equal itself, it seems silly that we even have to mention it, but in order to prove 2 triangles congruent, we need 3 pairs of corresponding parts, and this is the easiest pair to figure out, that one side is in fact congruent to itself, where it's the same length for both triangles. So now, if you would, circle statement 2, 3, and 4, and you see that you have 3 pairs of sides congruent, enough to justify that triangle JXL is congruent to KXL, and look what reason they used. Side, 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 or 3 pairs of corresponding sides are congruent to, in both triangles, So 3 sides in one triangle are congruent to their corresponding sides in another. Now try these A asks us to suppose that Greg knew instead that line LX was perpendicular to JK, and suppose he made measurements to find that JX is congruent to KX. Could he prove to his boss that the 2 triangles are congruent based on that information? If so, write a proof. So I'm going to work this proof out with you. We're using the same diagram, but different given information, so I'm just going to quickly draw it. So we got J, X, K, and L. And so they tell us that line LX was perpendicular to JK. So I'm going to go and mark in my diagram, if line LX is perpendicular to JK, that means that these 2 angles should be right angles, right? And then they also tell us that JX is congruent to KX. JX is congruent to KX. So let's think about how we could prove these 2 triangles congruent. Well, we have one pair of corresponding sides congruent, and we know that if this angle here, JXL is 90 degrees, and this angle here, KXL is 90 degrees, 2 right angles are congruent. And we also know, just like we used on this last proof, that LX is congruent to itself, as crazy as it is. So we actually have 2 pairs of sides congruent and the included angle. So we should be using side angle side here. So let's now draw up our 2-column proof. Statements on the left, reasons on the right. So statement 1, we're going to use our very first piece of given information. LX is perpendicular to JK, and that was given to us. Well, what did we discover after we figured out, or they told us that LX was perpendicular to JK? Well, that angle angle JXL and angle KXL are right angles. And how do we know that? Well, how do I know that this is a 90-degree angle? Well, that's the definition of perpendicular lines. Definition of perpendicular lines states that two lines that intersect or form right angles. So how did I know these two angles were right angles? Well, that's what perpendicular means. Well, if we know that these two angles are right angles, we actually proved a while back that all right angles are congruent. So then we can state, because the whole point of here is to prove two triangles congruent, we need to take step 2 and really emphasize if both of these angles are right angles, that angle JXL is congruent to angle KXL. It seems silly to mention because we know that in our minds, if both right angles, then they both have to be congruent. But we do have to mention it in the proof. So all right angles congruent. So now look what we have here. In step 3, we have a pair of congruent angles. So I'm actually going to circle step 3 because we're looking for 3 pairs of corresponding parts that are congruent. In step 3, we have our first pair. The next thing we can mention, because we've kind of tapped out that, is the second piece of given information. That line segment JX is congruent to line segment KX, which of course was given to us. I'm going to go ahead and circle that step because here we have 2 pairs of corresponding parts congruent. And then step 5, statement 5, we're going to go back to what we realized in the diagram, very similar to this example that they gave us, that line LX is congruent to itself. So we'll say line LX is congruent to line LX. And I'm actually going to, instead of saying congruence is reflexive, not that that's bad, I'm going to use reflexive property. Because reflexive property is actually used for equality or congruency. And now I'm going to go and circle step 5. So look at these 3 steps here. We have 3 pairs of corresponding parts congruent. We have 2 pairs of sides and an angle that's between them. So do we have enough information to prove the 2 triangles congruent? Absolutely we do. So step 6, triangle JXL is congruent to triangle KXL because of those 3 particular pairs of corresponding parts, which was 2 sides and an included angle. So we're actually going to use these congruence criterion to prove triangles congruent. That's the whole point here. Then B says that suppose Greg knew instead that line LX bisects angle JLK, could he prove to his boss that triangle JXL is congruent to triangle KXL? So let's think about that one for a second. So on B, I'm just going to draw it real quick. So I believe this is X, this is J, K, L. So they said that line LX bisects JLK. In other words, this angle here will be congruent to this one. So we have 1 pair of congruent angles. The other piece of information that they don't have to tell us, that doesn't have to be given, is that line LX will be congruent to itself. And so look what we know. We have 1 pair of corresponding congruent angles, and we have 1 pair of congruent corresponding sides. Is that enough to prove congruency? Well, again, you probably say, well, this angle's a right angle, this angle's a right angle. Not necessarily. In B, we turn the corner and say, hey, we don't know line LX is perpendicular to JK. So based on what's given, or what we can know from the diagram using for reflexive property, is that enough to justify that the 2 triangles are congruent? The answer is a big fat no, right? 2 pairs of congruent corresponding parts is not enough to prove triangles congruent, or at least not yet. I'm going to just leave it at that because we will see as we roll into 11.4 how that can change just a little bit. So this is the end of the video. Be sure to complete the lesson practice watch the video again, especially if we're struggling with proofs. Rewatch this page here, page 158, and go back to your learning targets and reevaluate your understanding of Lesson 11-3. Thanks for watching.